Hello everyone, welcome to our IEEE Communication Society podcast number 14. And as you could see that we had another episode, which was episode number 2, with Professor Marco Di Renzo from Paris Secular University, and it was one of the most watched videos and most listened podcasts. So just continuing that trend, we welcome again Professor Marco Di Renzo to our podcast now, and to talk about new developments, new things, new research that has been happening in this topic. Because again, a lot of people have been wondering about what has been happening. It's been 1 year, right, that since we recorded that. So I mean, we will want to talk about race topic, some other advancements, and some latest developments that we have done. So as we go through the conversation. So with this, I welcome Marco.
Thank you very much.
To this podcast.
Thank you very much for having me again. It's a great pleasure to be back.
Thank you for joining. Thank you. Yeah. So let's just start with something that where we left off in our last podcast. So we did discuss about the future of risk and also what was happening around that time, let's say last year, in terms of standards activities, and a lot of research was going on around reconfigurable intelligent surfaces, risk that I'm saying. So what do you think, what are the changes that have happened over this past year in this technology, and any use cases, applications that have been updated around this technology? So if you have any comments about that, Michael.
Yeah. So it has been a very exciting year. I would like to say. From the last time that we saw each other to record the podcast, there has been a lot of work on reconfigurable intelligent surfaces from academia, from industry. The pre-standardization activities are still ongoing, and the number of partners, industrial and academic, are growing. I think that the next year will be very, very important, I think, for 6G in general, because there will be some key events in terms of standardization. So I think that everybody is working hard and preparing some new results to see what we can do with this technology. So recently there were some publications from companies, Huawei, China Mobile, for example, who performed some system level studies about this technology, showing that even with realistic parameters that are typically utilized within 3 GPP, for example, RIS can provide some gains, which are not negligible, and I think that this will be a very important point for the discussions for the next meetings. Of course, it's very difficult to say what in the end the gains will be, but I think that this is at least one initial and promising research study. So I think that as far as only RIS is concerned, so surfaces that are distributed throughout the environments and can reflect the signals or refract the signals to optimize the propagation of waves. I think that there has been a lot of progress. Of course, the research community is still excited, so we can see many research papers. I guess that at least from my perspective, as an academic, I guess that RIS is a topic that allowed us to understand that we may be able to change how future networks might be designed and optimized. I think that one of the main things that RIS brought to the field is that some of the functionalities, maybe all the functionalities would be too much, but some of the functionalities of a typical wireless networks could be implemented in the electromagnetic domain, or what people call in the wave domain. And so there has been major progress in trying to propose new technologies that move from RIS, but try to further enhance the capabilities of this technology to manipulate waves.
Yeah.
On the one hand, I mean, not only surfaces that are deployed in the environment that can control the reflections. Even though, I mean, the technology itself is called reconfigurable intelligent surfaces, most of the applications so far have been on reflection, so controlling the reflection on signals, because it's a very practical, it's easy to deploy, and so we can clearly see the benefits. But we really understood that this could be, especially because of the progress in the field of metamaterials and programmable metamaterials. I think that we understood that RIS could be a platform that could do many things. It could not only be deployed throughout the environment on a wall or on a window to enable outdoor to indoor communications.
Yeah, like we could put it here,
also,
let's say on this wall, and probably reach the other corner of the room using reflection.
Exactly.
Something like that.
Something like that, yeah. Really to enable, for example, the communication between a base station and an indoor user, or to enable indoor to room-to-room communications in indoor. But I think that we also understood that we could utilize it for even to better design base stations or transmitters. So rather than utilizing it as a controlling the environment, but really as a technology that allows us to do typical beamforming at base stations. But with some advantages in terms of complexity reduction, in terms of reducing the power consumption. And in this direction, for example, there has been a technology that people have been developing, and we have shown that it can provide some benefits.
Yeah.
Which,
I think before you touch that, so I mean, just to summarize what you said, is that RIS was actually a good starting point to basically come out with all this reconfigurable transmission and reflection. And using the properties of metamaterials to basically enable sort of dynamic beamforming or dynamic sort of signaling that we were requiring, changing the sort of playing around with the propagation environment a bit, where you want to reach your signal towards any intended direction of user, let's say, right? But there was some doubts, there were some doubts from the industry and from let's say standards people that, look, we have some similar technologies in the past with our 5G infrastructure and, even before that. So why do we actually require something new and something to replace, in our current infrastructure? So, I mean, it looked like that it has good potential in a way because, as you mentioned, several of the sort of benefits of the technology itself, and we are working towards making low complexity solutions and energy efficient sort of beamforming and many other aspects like that. But we do require some more advancements. I mean, when I talk to my industry friends and colleagues, so always it happens that the RIS is good. I mean, okay, we have seen a lot of theoretical papers and lots of things, but what's next? I mean, what kind of direction we are following after RIS? So I think you were kind of to reach at that point. So
So in terms of RIS on itself, I think that what we really miss is this accurate and realistic evaluation of the performance with very realistic system level simulators, etc. So the most recent results was actually obtained by China Mobile. It has been shown that even if we consider intersite base stations of 500 meters, we operate at 2.6 gigahertz, and the panels, I mean, the RIS are not so large, but are realistically large. We can see from the system level point of view this 4 to 7 dB gain, but I think that we need many more studies to really convince the industry and people that this is actually results that
I mean, you can see like many of industry people have also adopted this sort of technology. I mean, in liquid crystal sort of based applications and many others. I mean, also the good thing was that these were inexpensive elements, and you could actually use them, for your test beds, for your, whatever the application that you were trying to provide. So, but the thing is that what's next?
Yeah.
To RIS? I mean,
So, I mean, I think that we really understood that reconfigurable metamaterials, or at least metamaterials in general. Yeah. Then, I mean, we can discuss whether in all the cases we need the reconfigurability or we need the reconfigurability in some specific cases. But we understood that the metamaterials could help us a lot to design future networks with some advantages, performance gains with respect to legacy technologies. One of these advancements, which goes beyond reflections, but it could be also utilized at the base station, is using multiple layers, multiple panels of reconfigurable metamaterials that are stacked. So basically, the idea is that the signal propagates through these layers, and while it propagates through these layers, we can process the signals in the wave domain and implement some complex operations, like some complex pre-coding that before we were predominantly doing in the digital domain. Now, this technology has been proposed recently. There is interest from the community, at least to understand what the potential, what the advantages and disadvantages are. It has been called stacked intelligent metasurface in our community. So,
so were you the one who coined this term, or
with collaborators? So it's always a teamwork. Yeah. So this is in wireless communications we like to use the term intelligent for structures that are reconfigurable and they can adapt to or control the propagation
and it's a nice
of radio
term.
waves.
You see, it's SIM. Takes us to the back days
SIM is a nice. SIM. Yeah, it brings us back to the
old memories.
To the old memories. Yeah, that's essentially that's good. Yeah, that's good. Yeah. And so, let's say that this technology itself, so having multiple layers of materials, it's something that studying a little bit through the literature. Yeah. It has been proposed in some early papers in different disciplines, but especially in optics. So at some point, people, it was around 2018, something like this, people proposed to utilize multiple layers of optical materials and to see how the lights could propagate through these layers, and then to implement some sophisticated operations. And so why this was proposed, and there are then some connections with what actually we are doing, but also some differences with what we're actually doing. Besides the fact that most probably in cellular networks we are not necessarily interested in the optical domain, but there are other differences. So the motivation was essentially that a multi-layer structure could somehow mimic the architecture of a neural network, of a deep neural network, right, or of a feed-forward deep neural network, to be more precise. So the intuition was that each layer of the optical material, or each layer of a reconfigurable or programmable metamaterial, could be viewed as one layer of a deep neural network. And each meta-atom, each unit cell of the metamaterial of this optical device could be viewed as a neuron.
Right.
So with one main difference. While the architecture looks like similar, so you have multiple layers that are connected through to the others, and the signal propagates in one direction from the first layer to the second layer to the third, and so on and so forth. Typical neural networks operates in the digital domain. So we take an image, we have a digital representation of this image, and then we do the processing, and we try to do the inference at the end, try to figure out what kind of image it is, or to do any sort of operations that we could imagine. Here the idea is that when the signal propagates from one layer to another, we stay in the wave domain. We stay in the electromagnetic domain. And I think that at this transition from purely digital implementations or predominantly digital implementations of wireless communications, moving towards RF or analog implementation was somehow facilitated by the progress that we have been doing, that we observed, that we obtained recently in the field of
we are moving back. I mean, from digital.
We are moving back
in a way.
Exactly.
Yeah.
We are moving back. Indeed, there is a nice paper written by one of the experts in programmable metamaterials in a microwave magazine that essentially claims this paper was written 10 years ago. It's a magazine, and he claims that we really should go back to analog signal processing because of the advantages that then we can discuss. And now analog signal processing could be an alternative to replace or complement all the digital signal processing that we have been doing. So now why? So the intuition behind the
so what's really the advantage we have in this?
So let's say the intuition behind the multi-layer. So why we need to go from one layer to multi-layer is the connection or the similarity with the deep neural network. Right. So we understand that having multiple layers, we can do more processing, better processing. But there are also some assumptions that we can discuss. But what could be the advantage of going from digital to analog?
Yeah.
So the digital implementation, we like it, is very good because it's very flexible. So we can really do many things. We have the capabilities of implementing many complex operations. But there is a price to pay, which is the complexity of implementing digital signal processors that realize all these operations. We need to have analog to digital converters, usually with a large number, with a large number of bits,
and consuming power consuming
that consume a lot of power.
Exactly.
Now, so there exist some scaling laws. Of course, when we talk about scaling laws, we always need to be careful because it's a scaling law. Of course, we need to do some accurate simulations and use accurate models. But there are, for example, scaling laws that tells us that the power consumption of an analog to digital converter increases exponentially with the number of bits that we utilize for the analog to digital conversion and linear with the bandwidth. So people over the last year have already been looking at this problem, especially when we started working on millimeter wave and then sub-terahertz and then terahertz communications, because people started wondering, maybe at those frequencies we cannot utilize full digital implementation, but maybe we should try to reduce as much as we can the number of bits. And many people are working on 1 bit ADCs for applications to millimeter wave, to sub-terahertz. So people started looking into these power consumption models for the ADCs.
I remember my PhD thesis included many years ago. These solutions.
Anyway, so we go back. Yes, we are learning from the past. Yes. So and essentially, this kind of scaling laws motivate somehow us to say, okay, if we could reduce as much as we can the bits, the number of bits, we could obtain this exponential-like gain in terms of power consumption. Now, as I said, this nice paper written by colleagues 10 years ago was already suggesting this solution. So why those days the community didn't go into this direction is difficult to say. One possible reason might be that the metamaterials that we have today, the reconfigurability that we have today, was not available 10 years ago. In terms of reconfigurable metamaterials, I think that RIS was motivated many people to look into the problem, and then there are now many more prototypes that were not available before. So we may have the feeling that even though we are still far from what we think a programmable metamaterial might be, but there are surfaces that could apply one phase, binary surfaces that can apply 2 phase shift, or even surface that can apply 4 phase shifts for each element, which has been shown not to be that much. So I think one of the main motivation is the possibility of reducing the implementation complexity, reducing the power consumption, and so to simplify as much as possible the architecture of a base station. From an implementation point of view, the easiest way, which may not be necessarily the most efficient one, but the easiest way could be to have a multiple metamaterial layers, to stack them one after the other, and then to just put them at the very close to the antenna, the antenna base station, and then when the signals are radiated by the antenna elements, they propagate through this device, and we do the processing.
I have 2 questions here, Marco. So first is that, you're saying that they can be put narrower and narrower, maybe the surfaces themselves, and also put them closer to the antennas. So is there any limit of how closer you can go? We have this antenna spacing lambda by 2, let's say, in general.
Yeah. So that's a very interesting
and
point.
also about the thing that how many of these layers we can actually use. I mean, what can be the limit to these layers? I mean, is it like a Massive MIMO sort of solution that you have, I don't know, like 250 sort of layers in one stack, let's say? Wouldn't this be too heavy to sort of process, or wouldn't it be like highly complex? So what are your thoughts on these?
Yeah. This is essentially the fundamental questions that the community is trying to solve. So let's say from an architecture point of view, I see this device as a hybrid MIMO solution, where we have a few RF chains. The number of these RF chains depends on the number of users, for example, that we want to serve. And then we have these large metamaterials with a number of reconfigurable elements in each layer, which can be much, much larger than the number of RF chains. So the advantage is a few RF chains, many elements.
So it looks like hybrid beamforming case.
It's an hybrid beamforming case implemented with a multi-layer architecture of metamaterials, because this multi-layer allows us to mimic somehow these DNN structures that we think could give us very powerful signal processing capabilities. Then we will see. Maybe I will first tackle your question, and then we will try to understand what the real differences or challenges with respect to real digital neural networks are, because we are very much far for saying that we are close to an actual DNN. But I mean, to get to your question,
it's evolving.
Exactly. We need to start from something. Yes. So your question, I mean. It's very important. So this is a technology that when it comes to deploying this device on close to the base station, so to implement this hybrid beamforming at a base station, operates in the near field. So we have the antenna elements very close to this device, and also the layers of this device could be a lambda over 2 or could be much at a distance, at an interlayer distance, which is much shorter than lambda.
4 or something.
Exactly, lambda over 4, lambda over 8. It really depends on the implementation challenges that there are inputting these layers together. On the one hand, we would like to, let's put it this way. On the one hand, we would like to put the layers as close as possible, because if we think of an antenna, of a base station, if we take this device with multiple layers and we want to put it in front of the antennas, nobody will accept to have a structure which will be 1 meter thick.
Exactly, yeah.
So, of course, I mean, if we are operated at sub-6 and we start having lambda over 2 and then we have many layers, this will be pretty thick.
But to be honest with you, I mean, you're talking about the base station aspect. It's a heavy sort of...
But
let's say if my phone I want to use same here.
I mean...
So how would I do that?
So essentially, I mean, the idea would be really to have this first of all, I mean, we don't need to have a very large number of layers.
Right.
Of course, I mean, the more the layers, what we have observed is the following. The more the layers, of course, the more the processing capabilities, but there is also a diminishing return law. So we don't really need to have a very large number of layers. So the layers could be 3, 4, 5. I think that we should spend more time to try to figure out how close these layers could be deployed, could be placed, because it's true that putting them at lambda over 2, spaced lambda over 2, will simplify the design, but it's also true that if we put them very close together, we have a structure that is not so thick, and also we could try to leverage the strong coupling between the layers, the mutual coupling between the layers, in order to have additional parameters basically to optimize.
Similar principles from wireless comms that we were using for antenna transmission, move it to these layers there.
Exactly. So and also, I mean, the elements on each layer could be put very close to one another in order to further enhance the performance. Maybe we could have closer layers, and with fewer elements, with elements that are very close to one another, we can reduce the size, and we can, in any case, do the processing by exploiting the decoupling between the elements. Now, experimental results recently. Some people conducted some experimental activities on this device with 1 layer, 2 layers, and 3 layers. And even though the device per se is not fully optimized at the moment, because it's one of the first prototypes. But the measurements show that if we consider layers that are too the spacing between them is not sufficiently small, lambda over 2 or even longer than lambda over 2, then I mean we could see some attenuation that kicks in, because there is an attenuation between the layers. And so, I mean, really, we have understood that the layers should be sufficiently close to one another if we want to leverage this structure, really to minimize the losses between the
layers.
Between the layers. So that's essentially something that has been shown recently, and so the results show that depending on the setup, we may have 3 layers, 4 layers, 5 layers, but I think that at the moment we miss, like I mean was at the very beginning for RIS, we are considering simple communication models that of course allows us to solve complex problems in communications, but we may oversimplify the electromagnetic characteristics of this structure. So in order to study all these trade-offs, how close the layers should be, how elements per layer we should put, and so on and so forth, I think that we really need to develop advanced communication models that originate from electromagnetics and that, like it was for RIS, will eventually allow us to understand what is going to happen in the near field, the real field between the elements, between the layers, and the near field between the unit cells. So I think this is good and bad in the sense that we can view now what I'm going to say in the positive way or in the negative way. The results that, one of the key properties of the deep neural networks is the nonlinearity of the neurons.
Definitely.
So thanks to the nonlinearities, we know that these devices, these structures, this architecture, the multi-layer architecture, can approximate very complex functions.
So these are also non-linear in nature when you deploy.
Yeah. So the
layers in the stack. Yeah.
Yeah. Exactly. This is essentially one of the key questions that now we start with. We are trying to study and to understand deeply, because most of the models all the studies actually that have been conducted so far, like it was for RIS, at the beginning, assume a linear communication model between. There are two main assumptions.
Yeah.
One is the linear communication model between the layers, and another one is that the transmission coefficient, because now the signal propagates from one layer to another, so it's not reflected anymore, but it really is a refracting structure. So the signal propagates, is transmitted from one layer to another, as an amplitude equal to 1, like it was at the very beginning for the RIS, where the reflection coefficient was equal to 1. Of course, starting with the simple point, which is having the transmission coefficient equal to 1, simplify things, because of course we are maximizing the transmission efficiency between one layer to another. But this also implies that there is no signal reflected back from one layer to another.
Exactly.
But to what extent we can design in practice a layer for which the reflection coefficient is exactly 0, this is a question mark.
Yeah. So it practically may not be that viable. Theoretically, it looks amazing, but
theoretically it looks amazing,
yeah.
But we need to take into account these signals that is reflected back. Now, this signal that is reflected back could create this back and forth signal inside this multi-layer structure. So the signal goes from layer 1 to layer 2, and then it goes back to layer 1, and then goes back to layer 2, from layer 2 to layer 3. So everything is coupled. Again, this is good or is bad. It depends on how we look at the problem. If we are looking at the structure that needs to feed forward the signal, so to propagate the signal from one layer to another, this is not good. But some people see into this the possibility of controlling the transmission and the reflection, and to design recurrent neural networks, because you include feedback into the system. Yeah. Now, how you stabilize it, how you control it, that's we need to see. Yeah. That's we need to see.
Understood.
But like it was with star RIS or Omni surfaces. So the having a reflection coefficient equal to 1 is good, but you are not able to communicate with the people who are in the other half of the communication coverage, and then people introduced the simultaneous transmitting and reflecting surface, which of course introduces some trade-offs, because you cannot send all the power in both directions. So there is an optimization problem. This is one point. The other point was this nonlinearity, which has been one main discussion. In the community since this technology was proposed into the optical domain. It needs to be said that people expert in developing optical systems, and which now this topic is called optical computing within the community, and there are also papers recently published in 2024 this year where people are discussing what the actual advantages of this optical computing is, and also what the role of reconfigurable metamaterials is. But let's say the nonlinearities has been there in the discussion for a long time.
Yeah.
Now there are people who are developing solutions that are non-linear. But what needs to be said is that in wireless communications at the moment there are not studies that consider the impact of the non-linearity. Again, this is good and bad. It's good from this point of view, in the sense that even though we don't consider non-linearities, so the system is linear, at least according to the results published, which are obtained under ideal conditions, of course, it needs to be said, but we see that there is a gain by adding multiple layers. We have this depth effect. So the fact that having a structure which a thickness with many layers, we could clearly see some benefits. And so the point is, if we already see these gains without using non-linearities, what kind of gains could we get if we consider the non-linearities, and if we can control these non-linearities? Now, indeed, as you were saying, the electromagnetic models for metamaterials are non-linear. And there are papers that are arguing on the inherent non-linearities of RIS.
Yeah.
So,
and also there are some distortions within, like your beamforming, your RF
processing
that you're using. They might not be perfect.
Absolutely, yeah. All this for
the take into account as well.
Yeah. I mean, it's a very long journey.
Like hardware distortions,
yeah.
they call it.
It's indeed a very long journey. So. Of course, now everybody is trying to show that under ideal conditions we have these amazing gains, because if we show these amazing gains and 10x factor and plus, then there may be some hope that in a more realistic setting we could see a few dB gain in practice.
Yeah.
But indeed, we should really develop these electromagnetic models and also try to see what these non-linearities are. So what is the equivalent for metamaterials on these activation functions that we utilize for deep learning? So I think that these are all questions that needs to be addressed. There are of course many others, but I think that as always, there are pros and cons. So to summarize, the ignoring the reflection is an ideal assumption, but we could try to engineer the reflections to design recurrent neural networks to add feedback, which in some applications have been shown to be interesting. And also we should really investigate this point of the non-linearities and try to figure it out. And in this, I think that the lesson that we learned from RIS is even more important in this field with multi-layer devices. Because RIS brought to our attention that we may replace some functions from the digital to analog, and when we can go back to the analog processing, as we were saying. But when we have waves that propagates that interact with the device in the analog domain, in the wave domain, we manipulate the signals in the wave domain, then we cannot ignore anymore the physical aspects that determine basically the propagation of signals and its performance. And so I think that RIS brought into the field this question, which is not a new question. It has been there since 1953 from the papers published by Dennis Gabor after Shannon paper, whether communications should be considered as a pure mathematical discipline, or it should be considered as a physics, as a discipline of physics. So taking into account these characteristics of the electromagnetic waves, so how the waves interact with the materials, the property of the materials, how the waves interact with the environments, if we deploy the surfaces throughout the environments. This multi-layer structure could also be put on a window or could be put behind a wall and could provide a boost of the signal from one window to another. It could also be put behind a wall and enable us to do image, so to sort of through the wall radar or through the wall imaging, detecting what there is on the other side of the wall, because we could boost the signal and also not only doing communications but also integrate communication and sensing together. So then we can elaborate this point as well. But from the methodological point of view, I think that RIS first, and then even more this wave domain computing, or wave domain processing, or wave domain computation, that this multi-layer structure that mimics deep neural networks brought into the field, I've also brought back the concept of electromagnetic information theory. So the fact that we need tools, models that take into account in a realistic manner the characteristics of the waves of the materials, and we cannot use two simple models purely based on a mathematical abstraction, because they are very powerful. They allowed us to understand the truly fundamental things and to optimize the communication systems that we know as of today. But maybe we need to do a step further. So indeed, there are now papers published also in information theory journals, magazines, titled Reintroducing Electromagnetics or Reintroducing Circuit Theory into Information Theory. Now,
it has to be a combination of all of these, using your communication fundamentals principles, use the electromagnetic wave theory, and also combine with information theory to come up with a good solution, which is perhaps less complex, or maybe can deal with all these probabilistic models, Maxwell equations that we're talking about.
Indeed. I mean, in the information theory community, I heard that many people call this electromagnetic information theory as a deterministic information theory, because you really move from the characteristics of the electromagnetic, the green function, let's say, so the typical representation of the electromagnetic, and then we do all the processing, we do all the analysis. Now, this electromagnetic information theory has been there. I mean, there are many papers published in transient information theory, transactional and transient propagations, that have defined and they have discussed what the role should be. Back in the days, there has been it has been primarily identified, electromagnetic information theory, as computing the degrees of freedom, so the fundamental performance limits,
the highest capacity possible,
in wireless communications or in networks. There are techniques that have been proposed. Now, I mean, I think that with the development of metamaterials, and especially reconfigurable metamaterials and their applications to wireless communications, this is coming back with a broader scope. While before it was only, or primarily, let's say, at least most of the papers that were published were focused on the computation of the degrees of freedom. Now, I mean, it's much wider. So it's, at least, I mean, based on my understanding, is taking into account the concept of near field, taking into account which was in part already there, the concept of near field, but to a larger extent, taking into account the concept of mutual coupling, all these things together, possibly even generalizing the approaches not to the typical line of sight channels without scattering, which is nice for people who work in the antenna field, but might not be sufficiently general for people who do wireless communications. So I remember that one of the the first papers on a electromagnetic model for RIS that I published with some colleagues, it was purely based on the line of sight. The reviewers were happy because of the novelty of the idea, but they also argued on, okay, but you need to make an effort to make it useful also for wired channel in the presence of multipath, etc. And then we worked on that, but as you said, we need to start from something. So I think that we should do the same. Now, I mean, there is interest from many people in our community, not only people in academia, but also several people in industry, and there is this term that has been utilized, that is currently utilized, which is electromagnetic signal and information theory. There have been special issues recently on JSAC, and there are other activities recently that started and that we can discuss. But first of all, I mean,
so why is this term? As it is.
Why like this? So I think that, I mean, this is my understanding. So even in the original, in the early papers, there was a discussion whether it was electromagnetic information theory or antenna information theory, because it was really depending on whether it was only focused on the antenna community or it was focused on the broader community of electromagnetic signal. I think that it's not only information theory, but there is also a lot of signal processing, in the sense that we can compute the fundamental limits and try to merge electromagnetics with information theory, but then we should also be able to develop the appropriate signal processing algorithms that leverage, that move from these models
based on compressed sensing or
exactly. So optimization, channel estimation techniques that takes into account
very
all
important
these
ones,
electromagnetics.
We need them.
We do.
Yes,
we do, and I think that it would be very nice if we reunite all these communities rather than just talking about the community of electromagnetics and information theory. I think we should put all the people on the table, and so I think making sure that people from electromagnetics, physics, metamaterials, information theory, communication theory, signal processing, the radar community, in light of the emerging applications and interest in integrated sensing and communications, etc. I think we should all go together. And indeed, I mean, one of the the reason why I think that the signal it's important is because we could develop accurate models for metamaterial aided technologies, let's say processors, communication systems. So we could do that. But then, I mean, when we talk to at least this was my experience with RIS. When you start developing these models, and then the next step is to use this model to do something, to do channel estimation based on that, to do the optimization of the precoding based on that, to do energy efficiency optimization based on that, all the things that we are used to do with the other models. But then when you talk with the community in optimization or in signal processing, they say, okay, but these models are much more complex than the models that we are used to use. We are used to our nice expression of the capacity formula with the log det. We have studied all the properties, so we know what we need to do.
But that's how the changes happen, you know. If you don't touch it, how do you know?
But there is the starting phase, which is difficult to convince people. So this is essentially, I think, the exercise that we need to, the change of mindset that we should have. So I personally, I mean, I was discussing with colleagues, close collaborators in optimization, and they told me, we would like to do this optimization, but it looks like quite complicated, because I mean, even if I compute the electric field from a dipole, and if I don't make any approximation, I end up having an integral. Then let's put multiple dipoles together, let's put multiple layers, consider the near field, consider the mutual coupling. So it start getting complicated. So, but recently, I mean, after some effort, indeed, we have shown that these models could be utilized also for optimization. So even the community in the signal processing, in the optimization theory, is now looking at this, and we are trying to work together to make it work. So I think that we should really look into the fundamentals of electromagnetics, embed or reintroduce, which is the right term, because the electromagnetic fields are what they are, so we just simplified them, but they are what they are. Reintroduce them into our information theoretic communication models, and then to do the effort to develop practical algorithms that we can see in a communication study. Of course, the information theory will give us what the best that we can do, which we need to know in order to understand whether there is a room for improvement by using practical algorithms. So that needs to be there. So I really think that all the communities should I mean, basically get together. It's not easy. We have seen that some of the algorithms developed could be utilized, but we need to apply new tricks. We need to apply new approximations, and I think that is an interesting. These are all interesting topics, in my opinion, for PhD students, for postdocs.
Yeah, it's a very, very new topic. I mean, would you like to mention our initiative on this topic, and maybe some latest developments that have been happening just very recently?
Yeah. I mean, as we were saying. This is a very recent and emerging technology, and also recently we understood the importance of going back to the fundamentals to develop new theories. So within the community, there is a tool within the IEEE community predominantly, which are called emerging technology initiatives, which is not only dedicated to technologies per se, but also to methodologies that could be applied to a large class of technologies. And one of the reasons why RIS became popular also within IEEE is because at the very beginning of its development or proposal, one emerging technology initiative was called ETI was proposed, and which was a sort of catalyst for all the people who were interested in working on the topic to meet, to organize workshops, to organize events at conferences. So it enabled a lot of networking opportunities.
Also in dissemination of the technology.
Dissemination, etc. So it was very, very interesting. Now, recently, in light of this generalization, if you want, of the risk concept towards not only a device that reflects the signals, but towards a computing platform. So I think we are moving from the concept of a device that reflects signals or transmits signal, but we are now thinking of a computing device that we can deploy through the environment, and that we can do whatever we want with it, like a deep neural network. A deep neural network, we can do whatever we want with it. We can do image recognition. We can do MIMO decoding. We can do channel estimation. We can do whatever we want.
Many things.
So we have this computing device, and that's the reason why I was mentioning this optical computing, which is not only related to optical things. It's famous in the optical domain, but it's doing computations in the wave domain, I would say, in the electromagnetic domain. So this brought the need, in my opinion, of federating the community around a new emerging technology initiative with a broader scope and more focused on, with a close look at technologies, multiple technologies, but also with a broader scope in terms of methodologies, fundamentals, also in an attempt to reunite these communities that we are talking about. And so recently the IEEE, and more precisely the Communication Society, decided to start to initiate a new emerging technology initiative just a few weeks ago, and which is indeed called electromagnetic signal and information theory. So
IEEE comes up ETI on ESIT.
Exactly. Yes. It's exactly. Exactly.
Advertise it a bit.
Exactly. Yes. And I mean, if you Google it, if you look, you will find a nice website that is available, and where you will find all the information, the upcoming events. And I mean, and if you are interested in joining, indeed, there will be an official kickoff meeting in a few weeks, in a couple of weeks, at IEEE Globecom in Cape Town. So if you happen to be in Cape Town, you are welcome, I guess, to attend this event. The event will also be you will also be able to participate to the event, to attend the event remotely. So there will be online participation for people who cannot attend physically. And I think there will be a great opportunity for all the people interested into these activities to meet, to discuss, to start planning activities together. It needs to be said that this ETI on ESIT is the results of a long journey, of a long process. There have been already at major conferences, ICC, Globecom, PMRC, etc., many workshops, and organized by the community. And it needs to be mentioned, in my opinion, that it was not only as one main thing when you start talking about electromagnetic signal information theory, that it would be a sort of niche dedicated only to the academic community, but indeed these events were organized, were promoted by companies.
Yes, a lot of industry people.
A lot of industry people were there. So most of the people who promoted were from companies, and academic people were invited as speakers, not as people who promoted initiated that. Exactly. So I think that we are. It's a very exciting time because it's a very exciting time because we are seeing that a lot of interest from industry in fundamentals. A lot of interest from people working in info theory, communication theory, signal processing, and a lot of interest from our colleagues from electromagnetics.
Yes.
So we can see that there are a number of special sessions, workshops on RIS, not only at ICC and Globecom, but at major conferences in the antenna community.
Exactly.
In photonics and metamaterials. So, and I think that this performing mathematical operations with metamaterials, which is what this SIM, stacked intelligent metasurface, may allow to us, is a topic that is getting interest from the community.
Yeah.
Of course, it's something that it might let us dream of, in the sense that mimicking, if one think, mimicking a deep neural network in the wave domain, it's something that it's very nice, it's very cool,
very fascinating.
Yeah, but of course, I mean, in between, having this nice idea or thinking of this possibility and then having it into a communication standard, it's something. It's a very, very long journey.
Yeah.
You don't know whether we will ever see this.
Perhaps next year we expect something we do not know, or in next release of the 3GPP.
I think that for the next release, if we can see RIS in its basic.
Yeah, no, I mean, we have had pre-standards, a lot of pre-standards activities on RIS already. I mean, we discussed in our previous podcast too. So it's not that it's a completely untouched technology. I mean, there is interest. As I was saying, RIS, there are companies that are trying to study them. Definitely.
Of course, I mean, there have been a lot of progress in RIS. I think that at least what we can hear discussing with the research community is that if we will see something in the next year within standardization bodies,
maybe some basic version of
of RIS, which is fine if we can get it, because I think that we need to bring the idea of into the community, into the standardization, and then we can move from.
In my understanding, Mark, I mean, because whenever I don't know, I go to speeches or when we are delivering our own tutorials and keynotes and so on. So always the impression that I've gotten is that RIS and the work around these technologies is very good. But we need to look for more variants of RIS to be able to see the difference, a major difference from what we actually use in our 5G infrastructure currently, like repeaters, relays or something. So how far we can go from there, and something that is more, let's say, concrete to be deployed into the network. So maybe holographic MIMO, for example. You have like large continuous aperture. It gives you this holographic sort of transmission reception. So it looks cool idea, and also it looks that it can make into the network the sort of deployment that we're talking about. Yeah. Then stacked metasurfaces or flexible metasurfaces that perhaps we can discuss in other podcasts. But also ESIT is an amazing term. So a lot of industry colleagues that I talk to, they are very intrigued by this idea of combining electromagnetic wave theory, information theory, and signal processing all together. And the good thing is, going back to our the initiative that you mentioned, the ComSoc ETI, that we are, yourself, I, and Ling Long are chairing with many other colleagues. So they're like close to 100 people, and I think there are 30 IEEE fellows as well. So you can see such an experienced team that we already have. So the good thing about that is that you have people from all these communities, like separate communities, and you bring them together for one goal, which is basically how to explore these electromagnetic wave properties and Maxwell equations, how to make them easier to solve. As you said, things are very complex. You need to consider many sort of constraints within when you are doing this transmission, reception, everything, right? And then at the same time, you also need to come out with good signal processing solutions. We are still figuring out whether we are staying in digital domain or analog, or like a combination of these, like hybrid, or what we are doing, right? So we are still in those stages. But the good thing is that many of these different communities are coming together from antennas and many other different fields, is for one common goal. So I do think that I'm very positive, I'll be very optimistic in saying this, is that maybe in next few years that we will see some very good developments in this field that we're talking about, the combination of all these ESIT that we call. That might make through into standards, into maybe start another pre-standards activity that can give a feedback to these standards that look, these are the activities that have been going on. And as you rightly mentioned, is that a lot of industry people have started this sort of initiative, right? This sort of technology. So it means that it's not just approximations and stuff on paper. People are actually interested to implement these as well and try out on their demonstrators, on their test beds and so on. So I would really agree with you in many of these aspects that maybe right now the picture is not so clear, but in few years we do hope that the sort of standard bodies or the organizations or the governmental people like who are going to implement these, or the industry stakeholders, whatever it is, that are going to take notice of the developments that have been happening, the sort of dissemination activities that have been happening around this technology, a lot of papers that people are putting through at the moment. But let's see what happens in next few years about this. So with this, I think one last thing I wanted to mention, Marco, if you would like to touch on that, is that we are also have an upcoming book on this technology. So I know a lot of things are happening, as many as we can touch. Yeah. So would you like to say something about that?
Yeah. This is a very nice initiative. So we have been working for a while with the support of many colleagues on a book. Many contributors on a book which in principle should appear in more or less 1 year from now. This is the target. So the book will have the same title as the ETI, so the ESIT, so Electromagnetic Signal Information Theory, and we have received a lot of interest from many colleagues, so who are very proactive. Even before inviting them, they heard about this possibility of having a book. So the waves propagated very well, and they approached us to contribute. So we will have a very large number of chapters, and the interesting point is that it will be very comprehensive because, as you said,
very expensive.
As you said, we received we will receive contributions from people from different communities, purely electromagnetic people working in electromagnetics and signal processing, in communication. So I think we will be able to touch all the possible aspects of this topic. And of course, we have 1 year ahead of us, so we will be able also to reflect to take into account.
I like to mention some people have already contributed, sent their contributed chapters already.
They have been very proactive to make sure that they are the first to promote some specific topics. This is. But we will try to see how as you were saying, is very important, the standardization activities, how they will evolve in this. Maybe the one point that I would like to touch is that in this perspective, I think I see a strong potential, many opportunities for the technology scene, but also for ESIT in terms of methodology in the context of ISAC, Integrated Sensing and Communications, because there we really see that that the communication aspects, but also the signal processing aspects could be fused together in one platform that essentially does computing without differentiating anymore whether this computing is for comm or whether this computing is for radar or for anything else. You do computing in the wave domain. You could do direction of arrival estimation. You could do communication, MIMO decoding with these general computing platforms and with the methodologies and tools that ESIT will give to you. From that point of view, there are pre-standardization activities on ISAC as well. There are standardization activities on ISAC. So I think that this technology could find a place in what is already been there, without forgetting that nowadays there is a lot of interest for many good reasons in developing sustainable wireless communication systems. And I think that, as we were saying, going back to the analog may be one possibility to reduce the power consumption, to reduce the complexity, to use some specialized materials that could be also friendly from the sustainability point of view. So I think that there are different directions that we could explore to see how this technology could impact. So I think that there are different options.
Perfect, Marco. I think this was the best way to sort of conclude the sort of remark that you made. But thank you so much for joining us at this podcast, and hopefully so that we will meet again and we will discuss more latest developments, and then we will see that this will be also one of the most viewed podcasts, I'm sure. And then we will continue our discussion in one of the next podcasts. But thank you so much for coming, Marco.
Thank you very much. I look forward to the next.
Yes, thank you
so much. Take care. Thank you very much.